In this video, I want to talk about memory arrays. Memory arrays are logic units that can help us efficiently store large amounts of data. So there are three common types of memory arrays. We can have dynamic random access memory, static random access memory, and read-only memory. So the general design or schematic of a memory array looks something like this. We have n bits of address, which basically specify the number of rows that we can have in our memory array, and each row has m bits of data. That this data can be either written on a row or can be read from that. So we have m bit of data value to be read or written at each unique n bit address. So there are generally two-dimensional arrays of bit cells. Each bit cell stores 1 bit of information, and as I said, we have n address bits and m data bits. So in total, we have 2 to the power n rows and m columns in the memory array. So depth is defined as the number of rows or number of words that are stored in the memory array. Width is defined as the number of columns or size of each word. And the array size in total is defined as depth multiplied by width. So let's take a look at a very simple example. So this memory array has only 2 bits of address. So with 2 bits of address, we can have in total 4 possible combinations. So that means that this memory array has 4 rows in it. And also we have 3 bits of data, which means that each row in this memory array contains 3 bits of information. So this is called the width of the memory array. The number of rows is called as the depth of the memory array. Let's just take a look at another example. So here we have a memory array with 10 bits of address and 32 bits of data. So this means that our memory array has in total 2 to the 10 or 1024 rows or words, and each word has 32 bits. So how are these memory arrays being created or being represented? So the way it works, for each bit we have a word line that is responsible for selecting a specific row in the memory array, and then we have a bit line that is either being used for reading or writing the data on the stored bit. So if we have a value 0 being written in the stored bit and the word line for this bit is 1, that makes the bit line to be 0, basically the value that is being stored. Or if the bit that is being stored is 1, when the word line is 1, the bit line for that specific bit becomes 1. On the other hand, if the word line is 0, no matter what is being stored in the bit line is Z or high impedance. So that means that it's not connected anywhere. So this is for one individual bit cell. So in general, we have more than one individual bit cells. So as I said, word lines are being used to address individual rows in the memory array. So they act like an enable signal. So basically, a single row in the memory array will be selected to either be read or be written to. Since this should be the case and at any given time only one row needs to be selected, that corresponds to a unique address. So each word in the memory has one unique address of its own, and only one word line is high at any given time. So since this is the case, we had a circuit component from before that actually had this capability. So if you remember, when we talked about decoders, we said that if we have n number of inputs, the outputs of a decoder are 2 to the n. And at each given time, only one of the outputs is 1. So we said that each output in a decoder actually representative of only one mean term, right? So based on that, by changing the address, we actually can control which one of these outputs are 1, or for this specific application, which word line is being activated. Because what we want is that for any given time, only one of these word lines need to be 1 while the other ones are 0. So let's say if we want to select these 3 bits, or basically this row in the memory array, since this word line 2 is connected to these 3 cells, that means that word line 2 needs to be 1 while word line 0, word line 1 and word line 3 are off. So that means that the combination in the input of this decoder that creates this word line or makes this word line to be 1 is 1, 0. So the least significant bit of the address needs to be 0, the most significant bit needs to be 1. So this is a bit cell representation of the memory array that we just saw here. So we have, for the first row we have 0, 1, 0 being stored. For the second row we have 1, 0, 0 being stored, and so on and so forth. So basically that is what we have here. We have, for the first row, 0, 1, 0 is stored. For the second row, 1, 0, 0 are stored. But now the question becomes, how can we make these bit cells or memory array cells? So in general, there are 2 types of memories. We can have random access memory, or RAMs, or we can have read-only memories, or ROMs. Random access memories are volatile, meaning that they lose their data when the power goes off. They are designed to be able to read the data and also write the data on them very quickly. So usually the main memory in any computer is the RAM. So this is historically called random access memory because any data word can be accessed easily as any other one. So there shouldn't be any sequence in the order of the data that you want to get access to. This is in contrast to the sequential access memories that we had back in the days, like tape recorders. So for ROMs, or read-only memory, they are non-volatile, meaning that they retain their data when power goes off. We can read the data from them easily, but writing on them is impossible or slow. And flash memory in cameras, thumb drives, digital cameras are all examples of ROM. But now you can see some discrepancy. Reading is easy and quick, but writing is impossible or slow. And one of the examples is flash memory. So there might be something wrong here. The reason is that these type of memory are historically called read-only memory because ROMs, back in the day when they were invented, you could not easily write on them. The act of writing data was usually happening during the manufacturing process or by burning fuses, which were not reversible. So once a ROM was configured, it could not be written again, or the process was very cumbersome. Of course, this is not the case for flash memory and other types of ROMs that we use today. But because this was a historically given name, it kinda got stuck on these types of memory. So now let's just see how we can actually create them. So for RAMs, we have 2 types of RAMs. One is called DRAM or dynamic random access memory, and the other one is SRAM or static random access memory. Their difference is in the way that they store data. So DRAMs use a capacitor to store some electric charge representative of the bit value 0 or 1, while for SRAM they use a set of cross-coupled inverters. DRAMs were invented by Robert Dennard in 1966, and as I said before, the data bit is stored in a capacitor. As you can see here, this is the generic design of a DRAM bit cell. We have a MOSFET transistor here that is connected to a capacitor. So if we want to store the data with value 1, we actually store some electric charge on this capacitor, and that is representative of a bit 1. If there is no charge here, that is representative of bit 0. So these type of random access memories are called dynamic because the value needs to be refreshed or rewritten periodically, and also after you read the data. So over time, because of the charge leakage from the capacitor, the charges decrease, so the data may be lost. Also, when you read the data, you actually destroy the value. Just think of it this way. If you had a glass of water, the only way that you could check if the water is in the glass or not, you drank the whole thing, right? You know that the glass was full, but now that you drank the whole thing, the glass is empty. So for the next person to know that it was full, you have to fill it again. So this is basically the concept behind DRAMs. Anytime you read it, you actually destroy it. So you have to rewrite it again. So that's why it's called a dynamic memory. On the other hand, for SRAMs, data bits are stored on cross-coupled inverters. So the generic design looks something like this. We have two MOSFET transistors, and in between we have two inverters that are basically forming a loop like this. Of course, the actual design of these memories is out of the scope of this course, but because of this design, a static RAM does not need to rewrite or refresh the data that often. So when word line is asserted, both NMOS transistors turn on and data values are transferred to or from the bit lines. So this is a very generic description of what's actually happening in DRAMs and SRAMs. For us, what is important is that they both act very similarly. They are there to store one bit of data. For ROMs, they were invented by Fujio Masuoka, and they are also very useful, and they have found widespread use throughout the industry. So right now the flash memory market is more than $25 billion per year. So let's just see how they are being created. So for ROMs or read-only memories, the bit cells are actually created by NMOS transistors, but the difference between storing a 0 or 1 is if we have the NMOS transistor in this configuration between the word line and bit line, the data is 0. If we don't have that, it means that the data is 1. So that's why writing on read-only memories was done usually during the manufacturing process, because for you to write something on it, you actually have to get rid of some components or basically burn a fuse, right? So this process was not reversible. But nonetheless, as you can see, the way that you use this type of memory is the same as the DRAM and SRAM. If you want to read it, you actually have to make this word line active. If you have this transistor there, that turns the transistor on, and this ground will be connected to bit line. If there is no transistor, the bit line, you can say, is up in the air, and that can be interpreted as having a 1 being stored. So usually for ROMs, we use what is called to be the dot notation. So anytime a transistor is not there, meaning that we have a 1 stored, we use a dot. Anytime that a transistor is there, meaning that we have a stored 0 here, we don't use a dot. So this is actually the way that we store data on ROMs, or at least we represent the data that is stored on ROMs using dot notation. So on the right, you see this data array that we have seen multiple times during this lecture. We have 4 words. Each word has 3 bits of data. So the first word is 0, 1, 0. The second one is 1, 0, 0. The third one is 1, 1, 0. And finally, the last one is 0, 1, 1. So as I said before, we use decoders to convert the address bits into a unique word line. And then by changing this, each one of these rows would be selected. So now to represent this memory array in a ROM or in using dot notation, since we know that each word has 3 bits, we draw 3 vertical lines. We know this memory array has 4 words. For each one, we draw 4. For each one, we draw 1 horizontal line, and each one of these horizontal lines is connected to one of the outputs of the decoder. And now anywhere we have a 1, we actually put a dot here. So for example, for data 2, which is this bit, we have a dot in the second row and the third row, corresponding to address 10 and 01. For data 1, we have 3 dots corresponding to the first row, the third row, and the fourth row, or corresponding to address bit 00, address bit 01, and finally address bit 11. And finally for data 0, we have only 1 bit, and that corresponds to address bit 00. So that's why we put a 0 here. Because of this property, we actually can use memory arrays to implement Boolean functions. If you remember, decoders were used to come up with all the possible minterms of a set of inputs, right? So that means that this part is basically the left part of any truth table, given a set of inputs. For the right part of the truth table, which was the actual function, we actually had to OR the minterms for which the output was true. So that's basically what's happening here. So if address bit is 01, address bits are 01, the output is 1, because we have stored the value 1 and it is represented by this dot here. If the address bits are 10, the output is again 1, because we have stored a 1 here that is signified by this dot. And for the other two combinations, the output is 0, because we don't have any dots, meaning that we have stored a value of 0. Now based on this, you can easily see that this is basically an implementation of a Boolean function in the form of sum of products. So if I just write it here, so data 2 is actually And let's just assume that the address bits are basically A1 and A0. So I can just put a comma between them, so you don't confuse that with being ANDed. This is actually a 2-bit number. So this corresponds to A1 bar, A0, and this one corresponds to A1, A0 bar. And you know from the definition that this is basically A1 being XORed with A0. What about data 1? Data 1 is the result of ORing these three output from the decoder, or more specifically these three mean terms. So it is going to be A1 bar, A0 bar, plus A1 bar, A0, plus this one, which is A1, A0. So as you can see, you can simplify this equation. So between this term and this one, A1 bar is common. Between this term and this one, A0 is common, right? So you can just repeat this term one more time and then do the simplification. And if you do that, this is going to be in fact A1 bar plus A0. But even this is fine. Basically, these two are practically the same function, even without the simplification. And finally, for data 0, we only have one combination of the address that makes the output 1, and that corresponds to A1 and A0 both being 0. So that corresponds to A1 bar, A0 bar. So we can use ROMs, or in general memory arrays, as means for implementing logic function. So let's just take a look at another one. In this example, we want to use a ROM, more specifically a 4x3-bit ROM, to implement these three functions. So X is AB. So the two address bits that we have, I just provide A and B as the address bits. So AB is for when A and B are both 1. So this is basically this min term. So I just simply put a dot here. A or B, it is for either A is 1, B is 0, A is 0, B is 1, or when both of them are 1. So this is for Y, which is A or B. And finally, Z is A, B bar. So when A is 1 and B is 0. So this corresponds to this bit here. So what we basically did was that we copy the whole truth table for these individual functions on the in the ROM. Anywhere we have a 1, we just put a dot. Anywhere we have a 0, we just don't put anything. We can do the same with any memory array. So it doesn't necessarily have to be always ROMs. We can use it with RAMs as well. Instead of putting dots, you just put zeros and ones. So here you see that we have two address bits again, A1 and A0. So for word line 2 and word line 1, we have stored ones for data 2, and for word line 1, 1 and 0, 0, we have stored 0. So this is in fact the implementation of this function that we just had here. So now instead of putting dots wherever we have one, I just stored 1. Instead of not putting anything, whenever we have 0, I just stored a value 0 in the bit cells. We can do the same example as before using memory arrays too. For x, which was AB, we store uh, one value in this bit for word line 3, which is for word line 1 1. Basically, both A and B are 1. For y, it is going to be 3 ones for these 3 rows, because if you remember from before, if we have A and B as the 2 inputs, we have 4 possible combinations. So if y equals A or B, it is 0 when both of them are 0, but it is 1 for all the rest. So these 3 ones are basically these 3 ones that we see here. One thing that you should notice is that there is no reason that you use this order, right? You can actually use the order that we had for the truth table as well. So this order is basically the inverse of this one, right? There is no reason to only do this. You can basically reverse the order, and now it is exactly the same as the truth table. As long as you're consistent, that should be fine. So this way of implementing functions is called using memory arrays as lookup tables, because what we basically do is that we copy the whole truth table in the memory array. So we look up the needed output for each input combination. So the input combination is basically the address, and the output of the logic function that we want is basically the value that is being stored. So you can add this to the several ways of implementing Boolean functions that we have seen before. So you remember we had two-level implementation, we had a straightforward implementation, we had implementation using multiplexers, implementation using decoders, and now you can have implementation using memory arrays added to that list. So in addition to the regular memory arrays that I talked about, we can have multi-ported memory arrays. So this is useful when you have, let's say, you want to work with larger array sizes, right? Or you want to have several read ports and, let's say, several write ports. So this is an example of a multi-ported memory array. So we have 3 ports. We have 2 read ports. A1, which has n bits, that's the address for reading data, and RD1, that is basically the corresponding uh, data that you read from address 1. Then you can have address 2, and RD2 is the corresponding data that you read from address 2. And then finally you can have A3 and WD3, which are basically the address port and the data that you want to write to for when you want to write a data into the array. And this WE3 act as the enable signal for the writing. So there are all sorts of different types of memory arrays that we can have. You can use System Verilog to define memory arrays too. So here I'm using System Verilog to define a 256 by 3 memory module with 1 read and write port. So if you remember, this was basically 2 to the power 8. That means that we have 8 bits of address and each word has 3 bits. So we have the usual module n module, the name that I gave this memory unit, dmem, and then for the sets of inputs we have clock and we, which is the signal for when we want to write the data. We have input logic inside the square bracket 7:0. That means that, and the name is A, so this is the address that we define. Then we have input logic inside square brackets 2:0, that's WD. That is the data that you want to write. And finally, you have output logic 2:0 inside the square bracket RD. That's actually the data that you want to read. So inside this, I'm going to define a logic value, which size being 2:0. So that's the size of each word. But for the size of the whole memory, we have 256 rows. So I just named this logic variable RAM, and I specify the number of rows inside the square bracket 256:0. So if I want to read anything from the memory, I just say assign RD, basically the output of this module, to be RAM inside the square bracket A. So any address that I give, the corresponding value in that address will be read and will be put into RD. On the other hand, if I want to write on it, I use an always statement, which is sensitive to the positive edge of the clock. So after the positive edge of the clock happens, if I want to write anything on that, on the specific memory cell or memory word, I first check the WE signal. Basically, that is the signal that tells me I want to write anything on the RAM. If this is true, RAM at location A or address would get the new value for WD, basically the data that I want to write on that location of the memory. So as you can see, we can use System Verilog very easily and very intuitively to create memory arrays.